Hi everybody. In our liquids and solids unit, we want to have a big review of some content that we've already seen, and we want to apply it in some new ways. So if you are thinking about today's video and feeling like a lot of it is very much review, you're probably right. So a lot of this might seem pretty straightforward based on what we've talked about thus far. So today we're going to have a review of forces and then talk about liquids. As a reminder, there are a bunch of different forces that exist both between molecules. We call those intermolecular forces, inter meaning between, like an interstate, and those that are within different molecules, we call those intra, or another word for that would be a bond. So let's review some of those forces. If you need to jump back to this page at any time, you can do that. This is a cool little diagram, so we'll come back and forth to here in a second. So let's first talk about bonds. There are three main types of bonds that we've discussed. They are ionic, metallic, and covalent. If you'll reference back to this little diagram I showed you, you'll notice that the bonds are all on the stronger side of the forces, right? So they're all stronger in general than the intermolecular forces, or IMFs. We're not going to compare a whole lot the relative attraction or the strength of these bonds next to each other, but remember that ionic things happen between metals and nonmetals. They result from a transfer of electrons, whereas covalent results from a sharing of electrons. So I'm just going to write those words in here to refresh our memory. So covalent is from a sharing of electrons, and ionic is a transfer of electrons from a metal to a nonmetal. And then metallic is kind of the sweet spot in between. Remember, metallics, the electrons aren't really directly shared or transferred, but they don't really belong or to any one given nucleus. They're able to flow from one place to another, and that's why they can carry an electric charge. Okay, so let's now talk about intermolecular forces, and as we're doing that, remember that covalent bonds can be either polar or nonpolar, which is going to help us to figure out the strength of the intermolecular forces, which is holding molecules together. So the weakest one happens between nonpolar molecules. Weakest ones are called London dispersion forces. They happen when, if you have two long chains of nonpolar molecules, let's imagine two long hydrocarbons, I'll draw them as zigzags. As the electrons in either one of those zigzags shift slightly to one side, so let's do that with a highlighter. If the electrons shifted slightly down to this side and at the same time slightly down to this side, then there'd be a little attraction there because you have a partially positive, well, not really partially, but just a slight positive next to a slight negative, and so there's attraction. But that's really, really darn weak when you compare it to dipole-dipole forces. Dipole-dipole forces happen in polar molecules. And the strongest type of dipole-dipole force is called a hydrogen bond, which happens when you have hydrogen bonded directly to nitrogen, oxygen, or fluorine, because hydrogen is so darn small, and nitrogen, oxygen, and fluorine are so darn electronegative. So remember, you might have something like water that has partially negative oxygens and partially positive hydrogens. And when you put that next door to another water molecule that has partially negative oxygens and partially positive hydrogens, there's a little bit of an attraction between those opposite charges. And so that's pretty darn strong for polar things and really strong for hydrogen bonds. And you might wonder, well, what if it's not a partial charge but a full-blown charge? Then if you had something like this, if we had, like, I don't know, sodium give up its electron and send it on over here to chlorine and become bonded together, that is a straight up ionic bond. So on our kind of range here, we go from London dispersion force is really weak. Dipole-dipole and hydrogen bonds is a specific subset of dipole-dipole. They're a lot stronger, but then really strong altogether are the bonds like ionic. So as a reminder, all of your IMFs are on the weaker side of things relative to your bonds. Okay, so let's talk specifically about liquids, and one thing that comes into play is called kinetic molecular theory, or KMT. So kinetic molecular theory, in short, means this. Kinetic means movement, molecular means molecules, and it's a theory. So we are talking about the movement of molecules, and in a nutshell, what we're saying is that if you want to get from a solid to a liquid to a gas, you need to add heat. Because if you add heat, heat is energy. The more energy that you give these particles, the faster they move, and motion is what causes things to be solid, liquid, or gas. And so for liquids, we know that these particles are pretty darn close together, right? They sit in the bottom of something like a water glass, but they are able to slide past past one another, unlike a solid. They do collide with one another. They collide with the walls of their container, and they have pretty strong attractive forces, right? Stronger than a gas, certainly, but not as strong as a solid. So that gives rise to some interesting properties of liquids. First one is viscosity. So things like honey or molasses are very viscous. We'll take a look in class at this article. This article is of a substance that dripped once in 69 years. So there's a big question, is that a solid or a liquid? But the fact that it did ultimately drip down from one place to another means that it's a liquid. It's just a really, really viscous liquid. It's maybe hundreds or thousands times more thick than something like honey, which we know is pretty thick to begin with. But viscosity is essentially a measure of thickness. And viscosity is dependent on intermolecular forces. So unfortunately, this graphic tells you that these have bonds, but really that word bond should say IMF, right? So this isn't a stronger bond, this is a stronger intermolecular force that's holding one molecule to another. So remember, bonds and IMFs are indeed different things. So the stronger the intermolecular force between different molecules, the better they stick together. And you can think about that as it goes from something like water to something like oil that is a little bit more viscous to something like syrup or molasses that's really viscous. It must have stronger intermolecular forces. Another property is surface tension. So we're pretty familiar with surface tension of something like water, and that is due to the polarity of those water molecules, right? So because there are these really strong attractive forces, again, they're IMFs, they're not bonds, so they're not as strong as bonds, but they're still pretty darn strong. They give rise to this really cool feature called surface tension. And one of the applications that causes is called a meniscus. So remember, with a meniscus, we have a situation where there's an attraction between the water and the glass of something like a test tube, and the attraction between the water molecules and other water molecules. So we have cohesion that's pulling this up, and adhesion to the glass that's pulling the water up the sides, and we get the little U shape. So that's why when we have a graduated cylinder, like so, we have to read from the bottom of the meniscus, but it always forms a meniscus because of this property of adhesion and cohesion. So that's just a little review